Welcome back, everyone. Today, we are popping the hood on something truly incredible. Ever wonder how massive data centers or giant power plants keep from literally melting down? Well, they completely rely on the absolute ultimate heat managers, cooling towers. Our title today sets the exact blueprint for what we're going to cover. We are breaking down the anatomy of these incredibly complex structures. We've designed this explainer to be super clear and really easy to understand, so we can finally unpack exactly how these hidden giants silently manage the massive heat of our modern world. Let's get right into it.
Okay, let's dive into this top-to-bottom spatial tour. We're going to start at number 1, the top air discharge system. Then we'll move down to number 2, the middle heat exchange system. Head further down to number 3, the bottom basin and piping, and finally, wrap up with number 4, the drive and control systems.
So, starting off with section 1, the top air discharge system, or as I like to call it, the exhaust. We're right at the very top of the tower here, and you can really think of this layer as the exhaust pipe for the whole operation. It's exactly where all that internal heat gets violently transformed into hot, wet air and pushed right out into the atmosphere.
To actually achieve that massive exhaust, there are 3 key mechanical steps happening at the summit. First up, the fan blade. It's often shaped kind of like an airplane wing to maximize efficiency, and it vigorously pulls or pushes the air. Second is the fan cylinder, which completely surrounds that fan. And get this, the clearance between the spinning fan tip and this cylinder has to be incredibly tight. We're literally talking millimeters here. Why? Because it prevents air leaks and crazy turbulence. And third, sitting just below the fan, we have the eliminator.
Now, what's really interesting about this slide is just how brilliantly simple the eliminator actually is. It doesn't rely on complex electronics or sensors. It purely uses physics. As that exhaust air rushes upward, the eliminator acts as a physical barrier, forcing the air to take a sharp, sudden turn. Because water droplets are heavier than air, their own inertia causes them to just smash into the barrier and drop right back down into the tower, while only the dry air escapes. It's like a giant physics trap. And here is why that simple physics trick matters so much. A high-quality eliminator reduces what we call drift loss to under 0.005% of the circulating water. I mean, that is practically nothing. But this isn't just about saving water. It's an absolutely crucial safety feature. By trapping those rogue water droplets, it stops dangerous pathogens, specifically things like Legionella bacteria, from aerosolizing and floating out into the surrounding neighborhood. Moving right along to section 2, the middle heat exchange system. If the top is the exhaust, this middle section is definitely the heart and lungs. This is where the real magic happens, the crucial evaporation and physical heat transfer.
Right at the top of this middle section, you've got spray nozzles firing hot water downward. But there's a massive risk we have to watch out for. The absolutely crucial point here is avoiding what's known as a dry spot. If these nozzles get clogged up with scale or random debris, the water won't spray evenly, so you end up with patches of the cooling tower that stay totally dry. And when air passes through a dry spot, zero evaporation happens. Honestly, it's a catastrophic failure because the entire system's efficiency just plummets instantly.
So, below those nozzles, the water hits the fill. That's the core packing material of the tower. Facilities basically have to choose between 2 main types here. On the left, we have film fill. This stuff spreads the water out into these highly efficient, ultra-thin films, which maximizes the surface area. Super efficient, right? But if your water quality is bad, it clogs up incredibly fast. On the flip side, on the right, we have splash fill. This is your rugged survivor. It literally breaks water drops apart by forcing them to crash into these grid structures. Sure, it needs a lot more physical space to work, but it survives dirty, high-temperature water environments like an absolute champ.
But hey, what if you're running a mission-critical server room? You absolutely cannot afford even a speck of dirt, scale, or debris getting into your unbelievably expensive internal chillers. Well, enter the closed-circuit coil. This thing is the ultimate data center savior. Instead of exposing the server's precious cooling water directly to the outside air, the water flows through closed copper or galvanized steel coils. The cooling tower just sprays its external water over the outside of these coils. This keeps your internal loop perfectly isolated, pristine, and totally safe from contamination.
All right, dropping down to section 3, the bottom basin and piping system. Or, staying with our anatomy theme, let's call these the kidneys. We've reached the holding, filtering, and balancing zone of the entire structure.
Now, this lower basin has a few core jobs to do.
First, the cold water basin itself acts like a giant bucket, collecting all that newly chilled water falling from the layers above. And since water naturally evaporates during the cooling process, a really clever float-operated makeup valve just automatically refills whatever water is lost. You also have overflow and drain pipes for managing any extreme water levels, and finally, a suction strainer. Think of the strainer as your very first line of defense. It filters out all the large debris, leaves, plastic wrappers, stuff like that, before the water gets sucked back into the facility's main pumps.
But I gotta say, the real unsung hero down here is the blowdown valve. Just think about it for a second. When water evaporates, the minerals inside that water don't evaporate with it. They get left behind. So over time, the water sitting in the basin basically turns into a thick mineral soup. That's where the blowdown valve comes in. It constantly monitors the water's electrical conductivity. When that mineral concentration gets dangerously high, boom, it automatically flushes that heavy, mineral-rich water right out of the system. This totally prevents massive, destructive scale buildup on all your expensive equipment.
Up next, Section 4, Drive and Control Systems, the brain and muscle. Now we're transitioning to the systems that actually power and regulate the entire tower. One thing you've got to note, these top fan motors must be incredibly well insulated. They require super high IP ratings, meaning they're heavily sealed against water and dust simply because they are constantly battered by a hyper-humid, chemical-rich environment.
And this brilliantly illustrates the massive shift happening in modern facilities right now. Historically, towers relied on legacy drives. We're talking belts and gears. They require constant tensioning, endless oil changes, and honestly, they suffer from terrible mechanical power loss. But today, cutting-edge data centers are shifting entirely to direct drive systems using permanent magnet motors. The motor connects directly to the fan itself. That means zero belts, zero gears, zero mechanical loss, and phenomenally less maintenance to worry about. It's a real game changer.
Plus, these modern motors use what's called a variable frequency drive, or VFD, and the math behind this is just stunning. Power consumption is directly proportional to the cube of the rotation speed. What does that actually mean for us? Well, if the outside temperature and humidity drop, what engineers refer to as the wet bulb temperature, and you slow the fan down by just a tiny fraction, your energy savings are cubic. It results in literally massive reductions in energy costs.
Another absolute lifesaver when it comes to control features is the Basin heater. This is basically a thermostat-controlled electric immersion heater that acts as a strict failsafe. Picture this: a cooling tower shuts off during the dead of winter. The water inside can quickly freeze, expand, and completely destroy the pipes. No way do we want that. So this heater automatically kicks in at exactly 4 degrees Celsius. It stops winter freezing dead in its tracks before it can take down your million-dollar infrastructure.
Section 5. Cooling Tower Maintenance Checkpoints. Let's tie it all together, folks. We've covered a ton of ground today, and if you want to keep this giant breeding machine running perfectly, you absolutely need a solid game plan. So for all you facility managers out there, here is your ultimate maintenance cheat sheet. Let's break it down. At the top, your focus is minimizing drift and checking for any weird vibrations. In the middle, you're on the hunt to prevent dry spots and scale buildup. Down at the bottom, it's all about cleaning out that sludge and managing your water conductivity. And finally, for the drive systems, focus on optimizing your energy through the VFD while keeping an eye on any oil or belts if you're working with an older legacy setup. These towers really are incredible feats of engineering, constantly balancing thermodynamics, fluid dynamics, and automated controls just to keep our servers humming and our lights on. But with AI and global data centers demanding exponentially more cooling every single day, it leaves us with a critical, burning question. As global data centers demand exponentially more cooling, how will the next generation of these hidden giants evolve to save our global energy grid? That is something the entire tech world is frantically scrambling to figure out. Thank you so much for joining me on this explainer today. Keep learning, keep analyzing, and I'll catch you on the next deep dive.